I think we are ready.
Okay, perfect.
Yeah, we are live.
Okay. So, good afternoon, everyone. It's my pleasure to introduce as today's speaker in the virtual seminars that our center is organizing, the researcher Olga Krali, a great scientist in the field of machine learning in pediatric acute leukemia. I've known Olga for more than 12 years. We studied together biology, and after that she obtained 2 master's degrees, and now she's a PhD student in Uppsala University. And she has experience for many years in machine learning. So today she will presenting her research entitled Deconstructing the Molecular Landscape of Pediatric Acute Lymphoblastic Leukemia using Machine Learning, a divide and conquer approach. The stage is yours, Olga.
Thank you, Mariana, for this great introduction. I'm really happy to be invited to this great initiative. I really like the fact that people from different backgrounds and different countries all over the world can share their knowledge and even be the beginning of new collaborations. You never know how that can turn out. At the moment, I had Mariana covering much of the stuff I wanted to talk about on my second slide, to be honest, because I wanted to describe my journey in research, as it was pretty complex to reach where I am today, as complex as the data I'm using at the moment are. So I started back in Greece together with Mariana. We both studied biology, but we took different ways. So I was specialized within the field of ecology and botany. So I went to Sweden so as to study ecology and biodiversity at Stockholm University. But back at the time, I started working quite a lot with data. So I decided that this is what I want to do for probably the rest of my life. So I started taking some freestanding courses in programming, as I had no background. And then I decided to start my master's molecular techniques in life sciences, which is a unique master's program that is a collaboration between the 3 universities at Stockholm, and is under the umbrella of Science for Life Laboratory, which is a great hub for research in Sweden. At the same time, I was working as an intern there at Child Life Lab, where I started to learn more about machine learning and data science, which helped me quite a lot to cope with my studies. And this particular master's equips all the students with all the necessary knowledge and tools so as to be able to analyze their own data. And there have been many of them graduated from this program that they work later on as data scientists or bioinformaticians. And at the same time, I was exposed to the teaching world through the so-called Vetenskapens or else House of Science, which was a unique institution employed university students so as to help school students so as to be exposed towards natural sciences and being inspired in a multidisciplinary way. After that, as I am a very curious person, I wanted to move on towards the industry so as to be able to see what's going on there and meet people who work within the engineering and programming fields to gain more knowledge. And I joined Ericsson and Capgemini, that they work with telecommunications and IT, more or less. But pandemic hit afterwards, and this is where the part where many people decided that they want to do different stuff in their lives, change jobs, even if it sounded pretty difficult. But eventually I ended up at Uppsala University, as a part of the molecular precision medicine group back in 2021. So now I'm on my 3rd year, and of course you can see a long line of dates, studying, and you might think my life is kind of boring, studying, but I have other interests as well. I like traveling, I like drawing, and during summer I explore the sea, and I love knitting during the winter. And of course I own a really large collection of postal cards from different countries in the world. And now it's time to talk a little bit about our molecular precision medicine group at Uppsala University. So it is a pretty recent group that was created in 2020 by my supervisor, Jessica Nordlund. And we are a very heterogeneous group. We are approximately 10 people, among which we are 3 PhD students, and we all have heterogeneous backgrounds, and our research is also very heterogeneous, and we cover areas including pediatric leukemia, autoimmune diseases, allergic inflammation, and we have some colleagues working in the lab constantly trying to improve or develop new methods so as to be able to analyze multi-omics data that they are constantly produced. But this is where I come. I'm working with machine learning specifically for pediatric leukemia, so I don't have experience over the other field apart from what I hear from my colleagues. And this is what I'm going to talk about today, focusing on our research and later on discussing a little bit one of our current works. So as I suspected, we are people of different backgrounds, and you might not know a lot about leukemia. First, I will go through some concepts about leukemia before stating the aims of conducting this particular research within this field, and I will briefly mention some of the materials and methods used before moving on to the results and discussion of the recent manuscript that we have prepared, and wrap up with some conclusions. So pediatric acute leukemia is the most common malignancy diagnosed in children worldwide and the second leading cause of cancer deaths in children. And as the name implies, if left untreated, the patients will die because it progresses really fast. So during leukemia, what actually happens is that immature cells, that they're called blasts, they grow uncontrollably, and as a result, they interfere with the normal blood cell production in the bone marrow and in the blood. And if the leukemia that includes immature myeloblasts is called acute myeloid leukemia, while the other one that includes immature lymphoblasts is called acute lymphoblastic leukemia, or ALL, which is the one that I'm going to mainly focus on today. And ALL is also divided further to BCP-ALL and T-ALL if it involves one of the two lines of white blood cells. So as you can see here on the right, I have a graph. So ALL is the most common type of leukemia and accounts for approximately 80 to 85% of new leukemia cases. And the majority of the incidents occur between 2 and 5 years of age, in contrast to the more rare AML that occurs between the first 2 years of age. And some information about what happens at the moment in the Nordic countries, because our cohort comes from the Nordics. So the ALL patients have been treated according to the so-called NOFO protocols. So those treatment protocols, they aim to facilitate risk stratification and disease monitoring, and it takes into consideration different variables, including white blood cell count, the age of a patient at the time of diagnosis, the cytogenetic subtype, which represents the oncogenic group a patient belongs to, as well as the minimal residual disease, which is the fraction of leukemic cells that they remain in the body during or after treatment. And based on these variables, the patients are stratified into standard, intermediate, and high-risk groups. So depending on the group a patient belongs to, they will receive the respective treatment. That might include administration of chemotherapeutic agents, targeted agents, in combination with corticosteroids, and some of the high-risk patients might even receive hematopoietic stem cell transplantation. So over the years, those protocols have been adjusted and have been improved, and that is shown in numbers. As we now, today, know that the patients that might suffer from ALL, they have like more than 90% chance of survival. However, while a patient relapses, their survival rate drops considerably. So one of the things that all protocols and all initiatives try to improve is to reduce the possibility of a patient to relapse. But at the same time, as those treatments have become more intense and more aggressive, some patients might experience short or long-term side effects that might affect their quality of life. And it's one of the targets is to be able to reduce those kind of side effects, not overtreat those patients. And one of the newest protocols is called ALL Together. It brings consortia from different European countries and tries to utilize information from retrospective cohorts from different studies so as to be able to better understand the different subtypes involved and also gain more statistical powering, especially for cases where we have rare subtypes, and help potentially any new ALL case that can be diagnosed nowadays in the clinic. But what happens with ALL? ALL is a very heterogeneous disease, and many different events might occur in different patients, and that define the different subtypes that are present. And it can include changes and numerical aberrations like extra or missing chromosomal copies you see in panel A, or intrachromosomal amplifications or other structural aberrations, including translocations, deletions, insertions, or inversions. And finally, those structural aberrations might lead to express fusion genes, where you have two or more genes that might fuse together, so they create hybrid genes that can be subtype defining. And then I'm going to talk a little bit more about why subtypes are important. But first, I will cover the part of what's going on in the clinics now and how you can establish these subtypes in the clinics, what methods they are now, and what's going to happen in the future. So at the moment, they're like traditional tests that they can detect those numerical and structural aberrations, including G-band, karyotyping, FISH, and RT-PCR. However, during the past decade, there has been this revolution with the introduction of next generation sequencing method, or else NGS. And for ALL particularly, there have been RNA sequencing and whole genome sequencing. And these methods allowed the production of a large amount of data, as well as identifying new patterns, new profiles that could help the identification of newer subtypes that weren't detectable before with those traditional clinical tests. And what's the current status of ALL? Now I present you the BCP-ALL specifically, because this is the type of ALL that has been well established, and there are a lot of different subtypes. At the moment, there are approximately 22 recognized subtypes. And in our Nordic cohort, we do have a representation of different types of operations that might occur, including abnormal chromosomal numbers, intrachromosomal amplifications, translocations that are also characterized by express fusion genes that they are subtype defining. And more recently, with the help of NGS methods, we do have some extra subtypes emerged that they can be different chromosomal rearrangements that are combined with express fusion genes, or the so-called like subtypes that they are very similar to the already established subtypes. In some cases, some point mutations can also be subtype defining. And here I have a survival plot where I actually want to show you why those subtypes are so important, and I'm talking about that the whole time. So here is our novel cohort that actually includes the pediatric patients from 1996 until 2013, more than 10,000 patients, and the event-free survival here that I have, the EFS, it is the percentage of survival over time, and represents the time, time interval between the diagnosis and before an event might occur. That could be like a relapse, to be a death due to toxic events, and many more others. So each one of these lines represent patients and their survivals, and they're color-coded based on subtypes. And as you can see, there could be like some subtype groups subgroups that they seem to do pretty well, but others that they don't do so well. And that's one of the reasons why subtypes are important, because they hold diagnostic and prognostic value. So being able to identify, to assign a correct subtype to a patient might help to give the appropriate treatment to them. But at the same time, we have a great issue, and it's something that happens across different cohorts in the world, not only in the NOFO cohort, is that there are a lot of patients that we call B-othe, which either those standard clinical tests fail to detect any recurrent chromosomal aberrations I mentioned earlier, or even the next generation sequencing method failed to find something that could point out towards a specific subtype. That could either mean that these patients might carry non-recurrent aberrations or non-detectable aberrations that might be detected in another molecular entity. And for the NOFO pediatric ALL cohort, this number is rather large. It's like 27% in the BCP ALL and 25% in the total ALL cohort. So the problem is that those patients, as mentioned, they are undetected, but at the same time, we have in our side NGS methods that they produce high qualitative data, including DNA methylation and gene expression data that can be utilized so as to identify subtype-specific molecular profiles, can be linked back to the subtypes. So there have been a lot of initiatives from different groups, including our groups as well, working with this type of data. And DNA methylation is a very important identification, and it's important for cell regulation. Of course, it's understandable if those patterns that exist for a specific region in the body are disrupted, things might not go well. So in cancer, what we actually see, what's the typical pattern is hypermethylation of those CpG-rich regions that they're called CpG islands, co-occurring with global loss of methylation. However, what is different from ALL is the fact that in ALL, their methylome is actually retains high levels of global methylation. And that was pretty interesting. What I can say at the moment is like in the current state is that we already know that ALL subtypes have been associated with DNA methylation levels. So in one of our older studies, as you can see here, what you can actually take, what's the take-home message from that? So here's a heat map plot ordered by hierarchical clustering for the 1,000 most variable CpG sites. And the red represents high methylation levels and the blue low methylation levels. And as you can see on the panel underneath, those are like the different subtypes that they are represented in the cohort. And we can see that there are subtype specific clusters where they have distinct methylomes, confirming this association between subtypes and DNA methylation. Similarly, with gene expression, we know that gene expression patterns are disturbed in cancer as well. Loss or gain of function of genes can lead to tumorigenesis, of course. And similarly to DNA methylation, gene expression patterns, subtype-specific gene expression patterns have been also observed. And one of the things that also have been found is those expressed fusion genes have been also associated with DNA methylation and gene expression data. And that's the nice thing while working with this type of information, because if you manage to build a model that is actually picking up this subtype-specific information, then you would be able to assign a patient to specific subtype, even if they don't carry any, or if any fusion genes were not detected, if they're not carrying any like recurrent chromosomal aberrations. And that's the magic of machine learning and why it can help to uncover these patterns on the data. But of course, if every time that there is like a solution, there is always a problem. And one of the major issues, many machine learning problems is this so-called curse of dimensionality. And that happens because we have a lot of features generated by those methods, like genes or CpG sites. And we already know that when you have like more than 3 features and you try to visualize them in it's almost impossible to get any particular to interpret those like features. And apart from that, the complexity increases. That might lead to high computational costs. That it's not the most desirable thing. And another problem, especially with bulk data, as like RNA sequencing data that we have been using as well, is that the sample size it's much smaller than the feature space. And that's a huge problem while training machine learning models, because it can cause the so-called overfitting. And by overfitting means that you have a model that actually memorizes the patterns in the data that has been trained so well, but when it is tested on new data, it cannot perform well at all. And that's not something that we want, because we want to make those models reproducible, of course. So later on, you will see how we try to deal with those issues. But I think it's really good to refer to those challenges since the beginning. So one of our goals throughout this project was to overcome biological and data complexity, and at the same time be able to map the molecular landscape of pediatric ALL using machine learning models built either on epigenetic or transcriptomic data for future precision diagnostics. And I have here a small overview of our large project. So the samples are taken from pediatric ALL patients, as I mentioned, treated in the Nordics, and they come from bone marrow aspirates or peripheral blood. Those patients have been treated in this cohort, you might see patients that have been treated like from newer protocols and other from older protocols. So we have like, and it's one of the nice things that we have here, that we can compare and we can see how patient outcome has changed over the years. And we have a larger, relative large cohort of more than 1,000 patients. And as I mentioned previously, these B-othe patients, they are 25% of the total. And we do have multiple data modalities that have been generated from those patient samples, including DNA methylation data for the majority of the patients. Then we have RNA sequencing data for about a third of those patients. And additionally, we got mutational data, information about fusion genes and copy number alterations that also helped us at the end with decision making when it comes to the subtype. Eventually, for the machine learning part, we created 2 different instances. That it is the RNA sequencing model and the DNA methylation-based model. And we utilize the model that is called nearest rank centroid. I'm going to talk about that in the next slide. And those models have been trained on 17 ALL subtypes present in our Nordic cohort. So the end of the study was eventually to build a robust model that can actually reclassify all those B-othe patients, so as to be able to wrap up with a survival analysis and see how the different subtypes do over time. And here is just a simple table of like our patient cohort and how they're distributed across all the different subtypes. And you can see that there are some subtypes, for example, that they have like more than 200 patients, but there are other subtypes that they contain less than 10 patients. And that's not happening only in our cohort. There is like this tendency, because those are rare subtypes. So it's eventually more or less the same in other countries as well. But before I move forward, I would like also to discuss the different methods that we utilize to profile DNA methylation and gene expression. And for DNA methylation, we use 450K arrays from Illumina. Those were available back at the time. For those who might know and ask why not EPIC array, which is like a newer version. So 450K arrays, they help to interrogate the DNA methylation status of approximately 500,000 of CpG sites across the human genome. And it is a high profile, high throughput out profiling method It's cost and computationally effective, and it offers high coverage across the genome. And of course, it has been around for a very long time, and that allowed a lot of people to develop some interesting tools for data normalization and analysis. So with the help of the 450K arrays, we got as an endpoint a beta value matrix that takes values from 0 to 1, where 0 represents no methylation and 1 complete methylation. And that was the input to our model. And additionally, because this type of assay helped to measure the signal intensities for those CpG sites, copy number alterations could also be detected with the help of 450K arrays. So for gene expression quantification, bulk RNA sequencing has been utilized, and it is a method that actually allows novel transcript detection and gives the opportunity for quantification of rare or lowly expressed genes, and at the same time to detect fusion genes and somatic mutations that can also help for a subtype determination. So our endpoint was a gene count matrix, and we also got fusion gene and mutation information for some of the patients that we have in our cohort. And now, no, it's not the model yet. One of the things that might mess in quite a lot with our time, especially people working with bioinformatics or machine learning, is data pre-processing and data cleaning, which takes most of the time, I would say. So one of the major issues is batches. So for those who might not be familiar with batches, so there might be like many times where people might prepare different samples under different conditions using different instruments or utilizing different labs, and that might create technical biases that usually overpower the biological variation that needs to be shown. So this effect must be corrected. And here in those UMAP plots, I show on the left how our data, RNA sequencing data, look like at the beginning, before batch correction, and how well they overlap with each other after we correct for any kind of batch effects. In our case, was the library preparation for RNA sequencing. And one of the things that is also important to take into consideration, especially when you have a lot of feature, is probably do some pre-selection, as I call it, step, where you might remove features that they're not informative, so as to denoise the data somehow and make it easier to proceed further with your analysis. And now, for those who are not very machine learning people, bear with me. I'll try to explain how this mirror-stranded centroid classifier works. Has been developed by a team that they were actually working quite a lot with cancer data. So it has been around for quite a long time. So it is a 2-in-1 model, because it's actually, apart from training a model and assigning patients to different subtypes, can also help to reduce features and keep the ones of importance. So what I have a very simplistic example here. So the first cloud of observation includes patient values for a particular gene, let's say gene A, and each dot is like a patient value for this gene. And then the centroid represents the mean of those observations. And for that case, I put like 1.2 here. So as the name implies, a shrink threshold that is applied actually tries to shrink the centroid or the mean towards 0. So for that example, the shrink threshold is 1.2 and the centroid is 1, the new centroid value will be 0. So apparently, what the model does is to iterate that over all classes, as you can see here on the table, and over all features. So for example, for feature 1, as we see in that example that I made up myself, is that after applying this shrink threshold, all centroids across all classes are constant and 0. Same for feature 2. We have this like number 1, like the value 1, to be constant across all classes. Apparently, for feature 3, we see that after applying the shrink threshold, it seems that something happened here for class 3. So probably this feature might be informative for class 3. So apparently the model, what actually does is to keep only the ones that they seem that they might play an important role for one or some of the classes, and leave out all the ones that they have constant values across all classes. And then it moves forward to the prediction step. And again, as the name implies, the nearest centroid, so as to make a decision in which class the sample X will belong to, it will count the distance from all the meets, and it picks the one that is closer. In that sense, it will assign the sample like with high probability to this class 1. And this is how the model works. That's the core of our like models that we have been building with either DNA methylation or gene expression as input. And here I'm going to present you some results from our recent manuscript that is now available as a preprint and is under consideration to a journal with the title Multimodal Classification of Molecular Subtypes in Pediatric Acute Lymphoblastic Leukemia. So based on the overview I gave you in the beginning, the materials and methods, more or less the same. So we use this patient cohort to build those neurostrength and centroid models that we collectively refer to as ALLIUM. And for those who might be known with like taxonomy, ALLIUM is the genera of garlic and onion. So I thought it would be a catchy name to give it, which stands for ALL subtype identification using machine learning. And apparently we tested the model in many different external validation data sets as well, before we move on and applying ALLIUM on the B-othe cases, so as to be able to solve the subtype for the majority of them. But as we already know, while building a machine learning model doesn't always mean that the information that will be picked will have biological relevance. So the model might be able to work well, but it might have picked some genes or CpG sites that might happen to explain the data, but not mean anything biologically. So what we wanted to see is like what it actually found. So I have highlighted from this plot, because here those box plots, they actually show either gene expression or DNA methylation levels for specific genes or CpG sites that they were selected by those neurostrength and centroid models across the different subtypes. So when you see the asterisks, it means that these signatures has been selected for that particular subtype. So for example, here you see these genes ABL1, PBX1, MEF2C, and ATM1 being key components of, so they were, how can I describe that? So there were subtypes like NATM1 rearrangement that picked NATM1 gene. So they were like picking the genes that they are like important for those subtypes, and they are like fusion, either partners of those fusion genes I mentioned before. So they show like that they were picked for the same subtype that they should. And there were other genes that they're like ALL related genes or leukemia related genes like CBPA or the HOX cluster gene cluster of genes that they're actually related to drug resistance as well, or Icarus that has been widely referred to many leukemia cases. So it seems that the model managed to also pick features of biological relevance. But when it comes to validating ALLIUM like as a classification tool, we actually utilized, apart from our, as I mentioned earlier, apart from our internal holdout datasets, we also utilized external validation datasets so as to be able to say with some confidence that the model actually works pretty well. And we saw that for the majority of the cases, we see that more than 80 or sometimes even 90% of concordance to the true ALL subtype has been observed. But that wasn't enough for us, so we tried like to find any other kind of models that have been around. For DNA methylation was kind of hard because there weren't any models apart from the ones built by our group. But for gene expression, there are a lot of different models. Among these, ALL sorts and ALL CATSAR, which are recently published. And what we actually did was to use those models and test the models on our own data. And what we actually saw is that they were more or less comparable, but there were some subtypes that didn't go well. So the classifiers, for example, the models didn't work well for this IM21. As you see, there are a lot of misclassifications, especially for that one that says that it cannot assign it to any class, doesn't know. Or for other cases where you do misclassification. So you assign it to a completely different class. And one of the things that we noticed here was this PAX5 group, which is a group of patients that is biologically similar to this BCR-ABL1-like or else Philadelphia-like group. Our model actually, in most of the cases, manages to correctly classify the majority of the samples, while the other two models, they actually do a lot of misclassification errors, as you see here and there. And they usually misclassify them as Philadelphia-like. And it might not sound pretty terrible, but considering that PAX5 is a good prognosis group and Philadelphia-like is a poor prognosis group, then it shows that if you have a model that cannot separate those subtypes, it might lead to for example, if this model was introduced in the clinics, to over-treatment of the patients because they would be considered as high-risk group. Finally, as I mentioned before, we have two different instances, the DNA methylation-based and gene expression-based models. And for some patients, we had matched DNA methylation and gene expression samples. So we wanted to see if ALLIUM actually works pretty well and what's the degree of concordance between the two different instances. And what we found it was that those two instances, they were coming to an agreement at 92%. So either using DNA methylation or gene expression for the majority of the cases reached the same result, which is pretty exciting because there are like two different type of molecular entities that they're actually giving the same outcome. Finally, after we validated the robustness of ALLIUM on predicting the cytogenetic subtype on ALL cases, we then applied it on the remaining of the B-othe cases. And what we actually saw, it was, as I mentioned in the beginning, 27% of BCPLL patients were B-othe, but at the end of the study, this number dropped to just 4%. And we see that many new subtypes were identified in this B-othe cohort, and that was done with the help of ALLIUM and also other molecular evidence, including mutations, fusion genes, or copy number alterations that help to further validate the model in a way that will make us to increase confidence for the predictions. So another thing that we did after patient B-othe reclassification was to merge those newly characterized B-others with the patients that we already knew the subtype at the beginning of the study and try to visualize the data. But we used the signatures that were selected by ALLIUM. So there were 519 CpG sites that were selected by the model with the method I previously mentioned, and 495 genes that were selected for the gene expression from the gene expression classifier. So on the left panel, we have all patients that for who we have DNA methylation for, and on the right one, all the patients with gene expression data. And we see more or less a similar case where we see subtype-specific clusters. And another interesting thing that you can also see is like those like subtypes, they're biologically similar to the other ones that they have very close to each other. And you can see that they are pretty close to each other in space. However, they are like not completely overlapping, meaning that the model managed to identify signatures that eventually help to separate one entity from the other. And another thing that you might notice here is that, for example, for the DNA methylation part, we see two ALL subclusters, and similar to gene expression, we see two clusters here for this KMT2A group and the DUX4 group. And that's interesting because you see that when you see something in one type of data, doesn't mean that you will see the same thing on the other type of data, which might mean that some changes that might happen in DNA methylation level might not reflect on gene expression level and vice versa, which actually more or less explains why the divide and conquer approach than integrating all the data together and run a model. Finally, this is the end point of our project. Since we wanted to learn and determine the subtype of those unknown patients, so as to be able to see what's going on over time and what's going on while all these cases will be resolved. So on the left, the survival plots are about full cohort at the time of diagnosis, representing event-free survival, as I mentioned previously, on the top, and then overall survival, which is the time interval between the time of diagnosis and the time where death of any cause happens. And what I want you to take home as a take-home message from here is that this B-othe group. So apparently it shows that the B-othe group has relatively high event-free survival over time, and also a very high overall survival over time. However, when we move on the right, here are only the reclassified B-othe patients. We see that there is like a great variation in outcome, both for EFS and OS among the different subtypes, which shows patients of excellent outcome and patients of poor outcome. And that further confirms why it is important to know and correctly classify the patients at the time of diagnosis, so as to help risk stratification. And with that, I have reached to my conclusions. So we demonstrated the power of machine learning to resolve biological and data-driven complexity in pediatric ALL. Additionally, we validated, as other groups have done before, the association between epigenetics or transcriptomics and ALL subtypes. And we also showed that each data modality could reveal information that was not necessarily detected in other modalities. And I think with that, I would like to end up with some acknowledgements. So I would like to thank my supervisor, Jessica Nordlund, as well as my co-supervisors, all the members of our NPM group, as well as all our collaborators and former colleagues. Also, the Novel Leukemia Biobank for providing the samples, all the organizations that have been funding our research all these years, and of course, the patients and their families. So, thank you very much.
Thank you. Thank you, Olga, very much for this presentation. Are there any questions?
Yeah, I have some questions. Okay, so thank you very much for the presentation. So at first, I want to ask you if I have well understood, your machine learning algorithm is from like an unsupervised learning family. Is that correct?
Supervised.
It's supervised. Okay, so you are. Okay, so it's a classifier. So you have a cost function that minimize proposing the particular type of class. Is that correct?
Yeah, I mean,
okay.
It might be a bit confusing due to, like, I guess, the feature selection step that looks a lot like an unsupervised approach.
Okay.
Actually.
So this is the first things, and then. Have you got any problem with the fact that your dataset is quite unbalanced? Meaning that there are subtypes with low number of patients.
I see your concern here, and that was like my main concern, because so that we have like a patient group with just 3 patients.
Yeah, indeed.
Like, just put them on the classifier, because I gave a rough approach, but what we actually did was more complicated than that, because we didn't do a multi-class classifier rather than one versus rest all the time. So for that particular group, we had only 3 patients. So it's like extremely impossible to get something out of there, I would say. But the thing is, like, miraculously, I don't know how it worked. And as I showed you, this NATM1 group gave the NATM1 gene as one of the key genes. And we eventually found some patients in our group that we could verify that the classifier worked while using like molecular data. Further, like, you know, supported the decision. I would say, like, in the majority of the cases, I wouldn't expect to find something like that. I was like, like impressed and worried at the same time, because, and that's one of the problems, especially for those like rare diseases where you don't have enough statistical power and you don't have enough subtypes to work with. And it's one of our like main goals for the future. Try to find as many as possible, try like establish either collaborations or find more data from other countries as well, so as to get more, because that the fact that it happened once doesn't mean that it will always work, because in the majority of the cases it doesn't.
Yeah. That's quite impressive indeed. Or
pure luck, I don't know how it happened.
And I have a last question. So for the like B-othe type, which at the start, I mean, you don't know which real subtype is. And after you have reclassified it in other in the other subtypes, is there a way to check? I mean, how much this sample, B-type sample, is I mean spreaded over the other possible subtypes? I mean, you don't know at the start. You don't know to which subtype belongs a B-type patient. I don't know if he is correct. And then you reclassify it, and then I don't know, you obtain like a percentage of belonging to a class or a distance to this centroid. And I mean, you can check if this percentage or if this distance is like very near to a particular centroid or maybe it's more near to nearer to a centroid, but it's quite near to other. And have you checked this behavior? If
I mean, one of the things, and it is, I guess, one of the reasons why we tried, like, as I mentioned before, this one versus rest approach is like you have one subtype and you put everything else to be like they don't belong to this subtype to the rest group. So apparently what you got for this classifier is like probability scores to belong to this class, and then you have like one classifier for each subtype. That gives you the possibility to get multi-classes as well, and also no class if you cannot assign it to anywhere. So it works more or less with probability scores, and we got a lot of like cases where we actually saw 2 or 3 classes as potential classes. Yeah. And that's one of the major, I wouldn't say issues exactly, it is one of the things that we're looking on optimizing, because you might have 2 or 3 and then there might be like 90% to be both of them. Which one are you gonna choose? And we, at the moment, we use a very naive, I would say, method of selecting based on the highest probability score across all the classes, because apparently working on like all those internal held out and external held out, it shows that in the majority of the cases, the highest score means like the correct subtype. But it's not always the case. And another thing that we have, it's like some rare cases that they might have a primary and a secondary subtype, and the model might pick up both. So that it is the problem, because you might have the other patients that they carry characteristics of both subtypes, and then you push it towards one direction only. So I think those things need to be considered for like a next phase. But at the moment, the output of the model gives us like gives the user the opportunity to get like a CSV file as an output, so as they can see if there were multi-class predictions, what were the scores, not only the final like prediction. And I guess that helps. And it's like, if someone else thinks that you have to keep those 2, they can eventually keep at their convenience what works. But I would say that it's really good to find the best way to make this decision boundary when you say that this is like, you know, what it should be or not.
Okay, thank you very much.
Thank you as well.
Any other question? I would like to ask you something. It's a more generic question. I think it's the fear or the concern of some researchers. Do you think that your model or any other kind of machine learning model could potentially replace the existing models for determining subtypes or a disease in the clinics?
I mean, I would say yes and no. Yes and no. Depends, because at the moment there are no models, not even in the clinics. I mean, on other models that have been potentially trained on numerous types of data that you know that's 100% correct. You are like have zero possibility of error. So trying to talk to a person in the clinics and tell them like, okay, I'm going to give you a model, and then you will, you know, you will rely on this model to make decisions for the life of a patient. They would say no. So I don't know if it's in the future it will like work perfectly, but at the moment it feels like that could aid decision making, because they have years of experience and might know things that, you know, not even a model can know. But sometimes there might be cases where they could be very ambiguous and they might need some help. And especially when, you know, time is against them and they need to make a decision fast to save a life. So then I would think that it would be really nice to go side by side. And I would never say that, you know, this is like our model is perfect, take it. I think it's better to say you can use it in parallel with some other like methods that they can help you. So
it's like more useful than something that will replace eventually.
One of the things that might be replaced in the future could be those PCR methods, those standard clinical methods, but then you will have next generation sequencing prevailing in the field, and then you can utilize those data so as to make your models better and better over time, and you can use them like side by side. That could be a really nice alternative. But I don't think in the near future that anyone will trust completely a model, and I wouldn't trust it either. I'm like, and I was thinking about like, if I get something similar as a question to talk about ChatGPT, because many people might have used it just to see out of curiosity how it works. And there are many cases where I might ask it the same thing 2 or 3 times and I get a different answer. And sometimes that I know that the answer is not correct. They're like, oh, I'm sorry, excuse me, I did wrong. It's that and that and that. So, and that model has been trained in like numerous amount of data and still wrong. So yes, I don't think it will completely replace it for the time being, but it's good to have it because it's fast. So people might be able to utilize it anyways. I think it's useful. So.
Okay, I believe the same. So thank you very much. I don't know if there is any other question. I think we are okay.